Our last topic for this chapter, we're going to discuss electric dipoles. This is just a discussion. I'm not going to have you do any problems regarding dipoles just because some of the definitions, even for electrical engineers, it's difficult to wrap your arms around because some of the conventions, some of the definitions are kind of difficult to use and understand. So let's take a look at a dipole, and we'll have a negative charge and a positive charge that are separated by some distance. And we'll have a vector going from the negative charge to the positive charge. That vector is the dipole moment, and we represent that with vector p, and we have some length L. Now, if we have this dipole inside of a uniform electric field, and let me draw this here. What will happen is that the positive charge will want to go with the electric field, and the negative charge will want to go away from or backwards from the electric field. And I'm going to have my moment or dipole moment vector. So we define the dipole moment equal to Q times my L vector. So we can consider this a vector and direction. And torque, because once we get this action of two forces working in opposite direction around a center point, the torque is going to be equal to the dipole moment cross product with the electric field. Remember, cross product is the vector that's going to be coming out of the center that's going to be orthogonal or 90 degrees from the moment of inertia. I'm not, sorry, dipole moment. And we can substitute in from this previous. Q is just a constant, and we have L vector cross E vector. And torque is a vector. If we want to know the absolute value of the torque, or just the value, not direction, that's the dipole moment times the electric field times sine of theta. Alright, so we've defined the torque. Now let's define the work. The work to move that dipole is going from angle theta 1 to theta 2 minus the torque d theta. And that's just going to be equal to negative of the integral theta 1 theta 2 dipole moment electric field sine of theta d theta, and I can take the negative sign out, and forgot, I can take the dipole moment and the electric field strength out, and that just leaves me with the integral sine theta d theta. The integral of sine theta is negative cosine theta, so that's going to take away this negative sign. And this is just going to be equal to dipole moment times the electric field cosine theta 2 minus cosine theta 1. And the potential is just the minus of the work, and that's negative dipole moment times electric field cosine theta 2 minus cosine theta 1. Now here's where the convention gets crazy. Basically, we make the potential equal to 0 when theta 1 is equal to 90 degrees. So when theta 2 and theta 1 are together, 90 degrees, that's going to be 0. And then if that's the case, then we say that the potential is equal to the negative of the dipole moment times the electric field times the cosine of theta. And that just makes the, you can actually put this in vector form. The cosine with the magnitudes of two vectors is just the dot product. And remember, the dot product gives you a scalar, so the definition is complete. And if I want the max or the minimum potential energy, it's going to be negative dipole moment times the electric field, and the maximum is equal to dipole moment times electric field. This is the part that's confusing, because how can you have negative potential energy, or how can you get to this transition? This is confusing to most people. So I tend to not require problems for you to do problems with dipoles, but it's a good for you to know it. If you get into electrical engineering later, then you'll get more deeply into this. I don't want to confuse you a lot more until you really need to. If you're in chemistry and biology, you'll never probably use this. So um, that's my take on it, and I just want you to know about it.